Thank you, Zongwei. So, okay, today I will talk about two works. The first one is Label Critic, which was presented at ISBI 2025. And the second one is Report Supervision, which was just accepted for MICAI 2025. The general idea of this presentation and what they have in common is the first one, we are trying to improve medical data sets, and the second one, we are trying to improve the medical segmentation AI. So let's begin with Label Critic, which is the ISBI work about improving medical data sets, specifically organ segmentation data sets. So what is the problem we are trying to address? What are we trying to improve? So let's begin with an overview. If you look at this plot, you see the sizes of CT scan data sets over the years. And you see that for almost 10 years, the size did not increase much. We had tens or at least a couple hundred CT scans in these data sets. However, in the latest years, the sizes were exploding. They are increasing very quickly. And now today we have public CT datasets with 10,000 CT scans and 10 annotated organs. We are talking about 100,000 annotations. By annotation, I mean per voxel annotation or label. So it's basically the segmentation masks of these organs. And why or how can these dataset sizes grow so quickly now? And the reason is AI assistance. So here in orange are all the datasets created with the help of AI. And you see that all large ones were created with AI assistance. By AI assistance, we mean the AI will segment the organs, provide a first segmentation, and then radiologists will look at the segmentations and improve them, or will have some active learning most often. And okay, so what's the problem here? The problem is that AI makes mistakes, so it makes label errors, and we must find and correct these label errors. However, we usually ask radiologists to look through annotations and find these errors. But does this make sense? Is this really necessary? Because we all know radiologists are very busy, their working hours is very limited and expensive. And our question here is, for most errors, for many label errors, do we need really radiologists to find them? Or can we maybe use another strategy? Maybe something like ChatGPT. So, okay, let's start.
Sorry, a general point here is that you're describing this problem for vision for medical, but this applies equally well to computer vision data sets as well.
Yes.
It's perhaps surprising how many errors exist in existing data sets, and also annotating the world would benefit enormous, creating real-world data sets which use these techniques is also extremely important. So everything you're saying, for people in the audience who are, particularly those who are not in the room, it is, I think, important to realize that and think about how these things could be applied to natural images.
Yes, I agree. And okay, so let's try to understand how difficult it is to detect many of these AI label errors. Here I have an image taken from a high school book that shows the organs. So let's look at the liver. The liver you see here is in the middle of the abdomen, and it has a roughly triangular shape. Now look at this liver label here. Does it look like a liver? Is it triangular? Is it in the middle of the abdomen? For sure not. It's a round thing in the bottom of the abdomen. And we have the other example. So the aorta is a blood vessel that comes starts above the heart and goes all the way through the body. It's the red line here until the ends of the abdomen. And here the aorta seems to stop at the upper chest. So again, there's something very wrong. And the IVC is like the aorta, another blood vessel that also goes through the entire body. And here there's something strange. It seems to be cut in half, and a big blood vessel cannot be cut in half. So again, this is an error. So these are some examples of AR errors, AR annotation errors that are pretty obvious. You can look at a high school book, look at the overall shape of the organs and say, this is not right. So this would not need a radiologist to find these errors because they are obvious. Now, other examples. So here we show that with a very simple description of what the organ should look like, you can see what's wrong. So the stomach is a single organ, it's a single object. So from these two images, which one is correct? The one. Yes, exactly. Because this is a single structure. Here, obviously, we have two. Now, the liver, should be a triangular shape. So which one of those is correct?
The right one.
Exactly. This one has a strange thing here, which is actually the intestines annotated as liver. And the aorta, it should have a curve on top. Which one is correct? The one in the left that has a curve on top. So again, these errors are pretty easy to identify. And here you see, in many cases, it's easy to compare the two annotations, two labels, and say which one is the best one. And an interesting thing about these are not AI errors. Those are errors in human-made annotations. The other ones were AI errors. And actually, the first one is probably some post-processing error. So the human annotated the stomach, but in post-processing it got corrupted. Here, the human maybe select the wrong label for the intestines. So they were annotated as liver. And here is a region of interest problem. The human did not annotate the entire thing. He stopped it in the middle. So you see, finding the error may be simple. It seems many times very easy. But what if you have not 10 images, but if you have 100,000 images, like in modern data sets? Then it's easy, but it's extremely time consuming. So should we ask radiologists to do that? And we think not necessarily. So our objective here is to use large vision language models. So things like ChatGPT, but not exactly ChatGPT because ChatGPT is paid. But use these large models to find these errors at scale. So to look at the whole data set and find at least the obvious, the big AI annotation errors, which are actually the errors that will be the worst for the models you are trying to train these data sets. And with this, we want to reduce the radiologist workload. We want to easily find these errors, and maybe by comparing two possible labels, we can even remove them and select a better label for this organ. And our main idea here is that it's way easier to criticize than to create. I can find these label errors, but I cannot annotate these organs. But by looking at them, I can see they're wrong. And our hypothesis is it may be the same thing for ChatGPT or other general large vision language models. They are not able to annotate these organs, but they may be able to look at the annotation created by other AI and say if it's correct or not, or to compare two annotations and say which one is the best one. Here is some brief related work. So there are other works on finding errors in AI annotations. So many works, for example, will use inconsistency. So they will compare two AI annotations and see if they are consistent, if they are similar or not. And then if they are not similar, they will flag for revision. So this is the main drawback for this approach. It will not say which one of the two annotations is better. It will say only they are different. Now the radiologist must look and choose. In our data set, this means the radiologist would need to look at 10,000 annotations, which is still a very large number. With our methodology, we not only say these two are different, we say, okay, this one should be better. And also many methodologies that try to find errors, they are created for specific organs. So it's not very easy to apply them to new organs, to annotations of new organs. So either because there are some priors about the organ in their design, or because they were trained to detect errors in this organ. So if you train them to detect errors in some organ, maybe it will not generalize easily to other organs without another training. And here we use zero shots. So we create this methodology to detect errors and to be easily applicable to new data sets. So now let me explain what is Label Critic, what is our methodology. Our main idea is we want to give a large vision language model the labels, and we want it to either compare to or to say if one label is correct or wrong. We start with the comparative approach, meaning compare two labels, say which one is better. This may be used easily to detect errors as well, because you may have a data set. You can download a trained model from the internet, create alternative labels for this entire data set, and use this for comparison and find errors in your data sets. So there is a main problem if you want to give labels to the large vision language model. The main problem is for CT scan is that the CT scan is 3D and the label is 3D. But these models were trained with images, normally natural images, which are 2D. So the first thing we do is a projection. We project frontally the CT scan, creating an image that looks like an X-ray. But for efficiency, we do a very simple projection. Basically, we sum all the values of the CT scan in this frontal axis, take their normalize them, and select the correct contrast window to make this image be similar to an X-ray in appearance. And even the models sometimes think they are X-rays. And then we also project in the same way the label, and we create an overlay. So we have in the back the projection of the CT scan, and over it in red the projection of the label. We do this for both labels, label 1 and label 2, and we give it to the large vision language model and ask it which one is the better one, is the best one. This is the comparative approach. To make this more efficient, remember, we may have 100,000 labels to check. So many of these labels, most of these labels, we hope, are correct. They should have no errors. So in this comparative approach, before giving the labels to the large vision language model, we compare the dice or the intersection over union of these two labels. So if they are too similar, we just keep the comparison. There's no need to compare labels if they are too similar. We only compare if they are, if their dice is below a certain threshold. So this accelerates the process a lot because we have we have much less comparisons to do. And to ensure that the LLM is really, the vision language model is really looking at the image and trying to understand which one is better and not guessing, we have a dual confirmation approach. So first we run this pipeline and describes it will say which image is better. Then we invert the order of the labels. So what was label 1 now becomes label 2, and we run the pipeline again. So if the model says, okay, it's consistent, the two answers are consistent, we say, okay, it's not guessing. If it changes answer, we assume it's guessing, and we flag this case for radiologist revision. Also, we allow the model, we give it the option in the prompt to say, I don't know, these labels are too similar, I cannot say which one is better, or even to say both labels are wrong. And we also flag these cases, which are the more difficult cases for radiologist revision. Okay, and this is our non-comparative approach because I say if you want to check your data sets, the best way would be to try to create some alternative labels for it and ask the large vision language model which label is better. But if it's really impossible to find a model to create these alternative labels, then we have also an alternative, which is this non-comparative approach. It's basically the same thing as before, but instead of asking the large vision language model to compare two labels, we ask it to check a single label and say if it's correct or incorrect. And a very important thing in label critic is the prompts. So this is where most of our developing time went. It was to develop a strong prompt because prompts really matter for accuracy. And we ended up with a three-step prompt. In the first step, we mostly want to know if the organ we are trying to check is or not in the CT scan. So, for example, you may want to know if the liver label is correct or not, but you have a CT scan of the head. And in this case, it makes not much sense even to do the comparison. So the first step we have here is we ask the large vision language model if the organ should or not be in these parts of the human body, in the parts that is represented by the CT scan. To do this, we do what I call a skeleton projection. So it's the same projection as before, but we adjust the contrast, actually the HU value window, to really emphasize the bones. So we give like an image of the skeleton of the bones that are in the CT scan to the vision language model. We ask it, what are the bones in this image? And okay, which organs are normally in this region? And should the liver, for example, be in this region or not? So this can easily detect errors like there's a liver in the head. Then, in case the model says, yes, the liver should be in this image, then we go for the comparison. And in the comparison, we provide the two labels, the projections, right? And we try really to give the medical knowledge to the model. So we find these general vision language models, they have varying knowledge of organs depending on which is the organ. So for example, for the liver, it's a model it knows well, so we can talk to the vision, it's an organ that the large vision language model knows well, so we can talk in a more high level way and specify which is how it's shaped. It's roughly triangular, it's near the just below the lungs, and the model will understand. For other organs like the IVC, which is a big blood vessel, then we go like we are teaching a middle school student. So we say, okay, this should be a straight line that goes from top to bottom, should have no cuts in the middle, it should be continuous. And we really explain to the vision language model how it should interpret this label and how can it say if it's correct or not. We really try to give medical knowledge and guide the model. And importantly, we also request the vision language model to give us a justification for its answer. So it will not only say this label is better, it can explain why this label is better. Then we come to the last step of our prompts, which is to ask the vision language model to summarize its answer in a template that we can easily process to get the information out. Okay, so now to the experiments. We did experiments in two large data sets. The first one is Abdomen Atlas. So we have two versions of Abdomen Atlas. The beta version of Abdomen Atlas and the first release. From these beta versions to the 1.0, to the release, we had many improvements of labels. So we have, for using these two versions of the data set, we have these pairs to allow the vision language model to allow label critic to compare and find inconsistencies. And this, with this comparison, we found there is about 1,500 labels that changed from beta to 1.0. And we use this data set to test label critic. So can it say which one of these two labels is better? And our second data set is Hopkins data. So we have the JHH, or the Johns Hopkins Hospital data set, that is a data set manually annotated by radiologists. So here we have very high quality labels, really better than almost all other data sets. And we created another version of JHH, which is a version created by AI. So we asked NNUNet to annotate all these organs in JHH. There are 9 organs that we used, and we compare the human annotations to the AI annotations. Initially, we were expecting only the AI annotations to have errors, but we found a few cases where the humans had errors, as I showed before, but the vast majority is AI errors. Okay, so now the results. We show that the comparative approach is very accurate. So using that prompt I explained before, we have the vision language model can explain, can say with 97.5% of certainty which one of the 2 images is better in JHH bench. And in Atlas bench, each case can say which one is better with 93% of accuracy, which is pretty high. Consider this is a zero-shot model, so it's a very easy to use approach. Now, to make this even more generalizable and easy to use for new organs, we have an organ-agnostic prompt. Basically, remove all the organ-specific information from our prompts, and we create a prompt that can be applicable to any new organ. So you can take this, and if you want to know if labels for a new organ that we did not test are correct or not, you can use this prompt directly out of the box. And with this new prompt, we have 82% accuracy in the comparative approach. For the non-comparative approach, by this I mean you just ask the vision language model if a label is correct or wrong instead of asking it to compare to labels. We have much less accuracy. We have 72% accuracy. This is the tail results if you wanna see. And another very interesting comparison. We have been talking about zero-shot vision language models, but you may ask, okay, which vision language models are you talking about? And all these results I showed before are for QN2VL from Alibaba, a model with 70 billion parameters, so a pretty large vision language model. And yeah, here I have its accuracy as I showed before in the non-comparative approach. So it's the smallest accuracy we have. Now, we show that this model, this large vision language model, is much more accurate than smaller vision language models. So Lava, with 8 billion parameters, had only 54% accuracy. So you have a big drop here. So it's important to have a large vision language model. And our next finding about vision language model choice is that general vision language models trained on natural images, so these very large, very diverse data sets of natural images, are much more accurate than medical vision language models. Meaning the vision language models that were trained initially on natural images and then fine-tuned on medical images. And this is pretty interesting. So these models, the medical VLMs, had basically random guessing accuracy. So LavaMed from Microsoft had 50.2% accuracy in the non-comparative approach, and M3D had 49.4%. And that's very counterintuitive because you could say, okay, why a non-medical model is better than the medical model? And I think the reason is generalization. So these general models, they are trained in very large and diverse data sets. And when they are fine-tuned in the medical data sets, these medical data sets are much smaller and much less general. So these models lose some of its generalization capacity. And our task needs generalization because our task is looking at projections of CT scans with overlays of labels. This is not a type of image you easily find in medical data sets used to train these vision language models. So you need to be able, the model needs to be able to strongly generalize to work well in Label Critic. Okay, so here are the main conclusions of Label Critic. The comparative approach surpasses the non-comparative one. General vision language models can understand organ labels and detect errors in medical datasets. Label Critic generalizes to diverse types of error, so we could find both AI-made errors and human-made errors, even though we developed all of our prompts considering only the AI-made errors. General vision language models surpass medical ones, and large vision language models surpass small ones. All our code prompts and the paper can be found in this GitHub link. Okay. Now,
Can I get just a comment on this? I'm trying to think of other examples of problems that people in the group work on where this type of method would be good. So, for example, when we are trying to generate images using diffusion star transfer, and when actually, Zhou, particularly for you, when you're trying to do things with animals, one of the issues I remember was that the quality of the images often wasn't very high, and you were developing some algorithms for trying to, decide if the generated image was a good one or not.
Yeah.
Also bringing in annotators to look at it. But if I remember, it was difficult. The algorithms weren't working terribly well, so it required a lot of people doing annotation, time consuming. So if one has
Yes.
this sort of approach, could it be useful for that type of problem?
I see.
Right. You generate an image, you've got some examples of real images of the objects you want to generate. You generate them using diffusion methods or other types of things. You have a large vision language model, where, QNN, could be it. It'll be worked on real images. You could ask it which one's good and which one's bad.
I see.
Because I remember in your case, it seemed like, you did need a very large number of images to be inspected. Right. Anyway, that's one thing to think about. I'm not sure, does anyone else have any examples of this to name?
Yeah,
Oh,
I used to build an interface that can scalably analyze a large amount of pseudo labels generated by AI or collect from crowdsourcing.
Yeah.
I think that would be a possible solution if we have a huge amount of data that we want to analyze their quality and maybe correct their potential mistakes inside it.
sounds good.
So
Yeah.
yeah.
Yeah, the reason that we said, yeah, label critic is useful for those large amount of data collections. I'm not sure if it's applicable to the semi-automatic tools. Probably yes.
Anyway, yeah, but good. Thanks for the suggestions and something thinking about, because several things. Keyhouse project on whether it's generating something realistic. If you remember that was some year or so ago. There we had some algorithm which was actually quite effective at deciding whether the thing was correct or not. You were generating an image supposedly of a cat, you attack it, and then are you generating a cat in the image? So he had a robust cat detector, but maybe something like this would be better.
So like for animals, so can VLM understand the 3D animal pose label as a label?
It might be able to.
Okay.
You could give it a try, see if it does. We don't, I mean, the point, I guess this really depends on what VLM can do. And we don't fully know, he don't obviously know that, but it could do, it
Have
could
a
do
try.
a lot of things and could be better than everything else, other things that we've been trying so far for doing that.
I see.
Another project I can think of, but actually I don't think there's anyone here who's involved in it, is the adversarial examiner work to attack things in a test everything data set. So Cheng Wang had a paper that was subtly similar than that. You take an image generated by you try to attack a model, assuming it's been generated by data coming from a diffusion model, so you can differentiate everything. And there was this sort of the unpublished paper that Cheng was involved with Rama's group. But one thing they didn't have, unlike Qihao, was that they didn't have an ability to have a reasonably good algorithm test to say whether the thing is working correctly or not. Qihao at least had an algorithm that was actually quite efficient, but even so, I think 10% of the images had to be looked at by hand. And so since that project is being done this summer by Qihao and Patrick Lee, maybe we need to think about that.